Now let's talk about circular motion. First, we'll consider the case of a uniform circular motion. An object is said to be in a uniform circular motion if it traverses the circle at a constant speed. As the object moves in a circle, however, it is constantly changing its direction. We are now talking about velocity vectors. So that means in this case, even though the magnitude of the velocity is the same, its acceleration is changing all the time. The change in direction of the velocity causes the acceleration to change continuously. This acceleration is called the centripetal acceleration, and it's directed always towards the center of the circle, as is shown in the animation. Without this inward force or this inward acceleration constantly pulling this object towards itself, this object will not remain in a circle. So, for example, for this object, if it is moving in a circle and it encounters a scissor, what that will happen is it will start to move in a path tangent to where it was, and it will no longer continue to go in a circle. So now, what do we need to know in order to talk about rotational kinematics? In general, we so far have been talking about displacement, distance, speed, velocity, and acceleration. Same things will apply to rotational kinematics, however, their units and so forth will be changing. So for example, the displacement now will be represented as delta theta, which instead of being measured as a distance, it will now be the measure of the angle. The angular velocity will be related to the velocity, the linear velocity, but now this is going to be given in terms of omega, and acceleration is now going to be angular acceleration given by alpha. Now, let's talk about each one individually. Angular displacement. In order to define what the angular displacement is, or how far something has moved, we need to do two things. We need to do one, identify the axis of rotation and choose a line perpendicular to this axis. Then to observe the motion of a point of this line. So if you have a circle, what point should you start from? So scientists have just come up with a random reference line which corresponds with the zero line of when we start talking about angles, and this is what all angles are measured from. So let's say you have a disc, a CD, and you want to measure, and it is rotating around its axis. We want to measure how far or how fast this rotation is. What we do is we find a reference line, just like this one here, and then we find the angle that corresponds with it, and then we figure out another angle from the reference line, and delta theta, which is theta minus theta naught, will give us the angular displacement of the line. So basically the question is, how can one define the change of position of this point during the rotation? The simple answer is the change of angle the line makes with the reference line will give the change in position. So basically measure delta theta. So in order to calculate the delta theta for a uniform circular motion, theta is given by some final theta, where the line is at that point, and minus the initial one. So the angular displacement is going to be theta f minus theta I, where both theta f and theta I are measured with respect to the chosen reference line along the x-axis. Another very important thing to note here is angles are measured counterclockwise. Counterclockwise angles measured are always considered positive. Angles measured clockwise are always considered negative. And here's something I would suggest that you write down on a piece of paper and remember it. 2 pi radians is in radians the angle that the whole circle moves. It's 360 degrees, or it is also called 1 revolution. Please write this down somewhere. It is going to prove very useful when you're solving problems. In terms of angular displacements and angular velocities and angular accelerations, another term becomes very, very important, which is called the arc length. The arc length is the distance that your object, say, moved from here to here. Now notice that what it's doing is it's not following a straight line, but the line is actually curving slightly. This curved line is called the arc length, and the arc length is related to delta theta, which is the angular displacement, and r, which is the radius, by this formula here. Note delta theta is the relationship between these two ratios. This is given, the arc length is given in meters, and the radius is also given in meters. So delta theta basically is a dimensionless ratio. Angular velocity. Now, angular velocity is just like the regular velocity. It is a rate of change of displacement. But in case of the angular velocity, it is the rate of change of angular displacement. So the angular displacement is given by delta theta. So the average angular velocity is going to be given as a rate of change of angular displacement with respect to time. Instantaneous angular velocity is the rate of change of delta theta in the limit when delta t goes to 0. Now, another very important thing to remember is that omega is measured in radians per second, not in meters per second, radians per second. So if you see a unit like revolutions per minute or any other terms, you have to be able to convert it to radians per second. So an object moves along a circular path of radius r. What is its average velocity? So this is our problem we need to find out. So theta 1 and theta 2, delta theta is given by the change theta f minus theta I. So we know that V average is total distance over total time. So the total distance that it travels is the arc length, right? Which is r theta. So S equals r theta. So this is going to give us r delta theta over delta t. So V average equals r delta theta over delta t, which includes V equals r omega, which is the angular velocity. So hence the relationship between the average velocity and the linear average velocity and the angular average velocity is given by this relationship here. This is a very, very important relationship. You have to remember this. Instantaneous velocity also is given by V equals r omega, where V is the linear velocity and omega is the angular velocity. When we talk about circles, we have to talk about periods and frequencies. Period is the time it takes the circle one time to go around a closed path. So in order to calculate what the period is, we have to find the total distance divided by total time. Total distance in a circumference is always 2 pi r. Total time, if its period, is going to be called t. So if you compare it to V equals r omega, omega becomes equals to 2 pi over t, which equals to 2 pi f. So where omega is going to be called the angular frequency and f is going to be called just the frequency. And it is always equals to the number of cycles per second. And the unit of frequency is the hertz. It's Hz. Now let's talk about centripetal acceleration in a little bit more detail. So to keep an object moving in a circular path, you constantly have to change its direction. That means that even if the speed is constant, the velocity of that object is not. So if the velocity of that object is not constant, that means the acceleration is always changing, which means that the force is always changing according to Newton's second law. So that means we can conclude that in order to keep an object moving in a circular path, the object must have a non-zero net force that acts on it at all times. The centripetal acceleration is also called the radial acceleration, and the reason is because this acceleration is always radially inwards. It always points towards the center of the circle. And the magnitude of this radial acceleration can be written as A equals V squared over R, or as V omega, where omega is the angular velocity and V is the linear velocity. Now, the result of our discussion has been that we need a non-zero, a changing acceleration which results in a changing force. That changing force is called the centripetal force. And the reason why it's called the centripetal force is because it's a center-seeking force. Okay, so it'll always be pointing radially inwards. Mathematically, centripetal force is written as mv squared over r, or mr omega squared. So both of these will become very useful in order to solve problems. Now let's talk about units. For angular displacement, the symbol is theta. The units is radians. Angular velocity, the symbol is omega, which is radians per second. Angular acceleration, alpha, should be radians per second squared. Now, All of these are very similar to the linear case, and they are all related to the linear case. However, they are their own units, and they are their own symbols. So be very careful when solving problems. Conical pendulum. Whatever the nature or origin of the forces that act on an object in a uniform circular motion, the resultant of all forces must be in the radial direction and with magnitude F equals mv squared over r. A conical pendulum is a pendulum that you have a mass attached to a spring and it moves around in a circular path. That is going to be called a conical pendulum. The important formulas are speed of the conical pendulum and time taken for one complete revolution. Here I would suggest that you look at example 5.6 given in the book about conical pendulum. It is very important that you actually go over that problem yourselves.